Hello and welcome to Woven Chemistry. I'm Jean Weaver, and today we're going to work on creating lab procedures. And specifically, we're going to work on a lab procedure to distinguish three metal hydroxides. So maybe you're asking yourself, why should I watch this video? Well, this is really good if you're preparing for a hard test on stoichiometry, maybe titration, one with off-the-wall questions, or perhaps one that's got lab-based questions. All right, so let's get started. So again, here's our task. You're going to be given three metal hydroxides in solid form, and you have to write a procedure that will enable you to identify each hydroxide. Here are the materials that you have available. So you've got equal masses of each hydroxide: barium hydroxide, sodium hydroxide, potassium hydroxide. You've got some phenolphthalein, three 25 ml Erlenmeyer flasks, some distilled water, 3 stir rods, and some hydrochloric acid, but the problem is you don't know the concentration of that HCl. Here's a little hint. Barium hydroxide is a hydrate, and it has the formula of BaOH2 with 8 waters. Okay, now I really encourage you, pause the video, jot down your ideas for this. Okay, chemistry is about thinking and learning how to reason. It's unlike biological sciences where a lot of the times you just have to memorize stuff. The only way to learn how to think is to actually practice it. Okay, pause the video if you get stuck. I've got some hints coming up next. Okay, first hint, the molar masses are very useful. Second hint, the molar mass of barium hydroxide is a lot more than 171 grams per mole. Number 3, writing down the equations for the reactions of these bases with HCl is helpful. Number 4, did you balance those equations? You should get coefficients that are 2 or smaller. Fifth hint, what does that phenolphthalein tell you? What does its color indicate to you? And lastly, I'm sure many of you are frustrated and kind of stumped by the fact that you don't have the concentration of that HCl. It doesn't matter, okay? So figure out a way to use the rankings instead of absolute numbers. Okay, so moving on, we're going to work through some of the thinking and the numbers that we need to think about before we create the procedure. So here are the three compounds and their molar masses. Now with these molar masses, and if we remember that we have equal masses of all samples, I mentioned that we should go with rankings. We don't know what the mass is of each of the samples, so we don't know how many moles, but we can rank them. The molar mass of the barium hydroxide is really big, so that means we're going to have the fewest number of moles of barium hydroxide. Sodium hydroxide is the smallest, so that means we're going to have the most moles, and the KOH will be somewhere in the middle. Now let's try to get a little bit more specific, and let's call the moles of barium hydroxide X. Okay, now if we imagine, we could just kind of round, the molar mass of barium hydroxide is about 320. Well, that means that we've got about 8x moles of sodium hydroxide. And similarly with that KOH, we've got about 6.5 moles. So now we kind of have some numbers. All right, let's go a little further. We've got these balanced equations. They react in a 1-to-1, except for the barium hydroxide, which is 1-to-2. Well, that kind of makes things a little bit more complicated. So now let's think about that X moles of barium hydroxide. Since it takes twice as many moles of HCl, we could almost think of that as 2X. 2x moles of barium hydroxide. Okay, so now let's think about how much HCl is needed. Well, we have the fewest moles of barium hydroxide, so that's going to take the least amount of HCl. The sodium hydroxide is going to take the most, and the KOH will be right in the middle. So see what I mean? How we can use rankings instead of absolute numbers. Okay, so now let's go on with the procedure. So the first thing you're going to need to do is transfer each hydroxide to a labeled flask, add some distilled water, and stir to dissolve. Now maybe you're wondering, well, does it matter how much water I use? Well, let's think about that. Let's say we've got a big beaker full of 4 moles of sodium hydroxide and a small beaker full of 4 moles of sodium hydroxide, equal amounts of base in each one. For the big beaker, it's going to take 4 moles of HCl to neutralize that hydroxide. And the small beaker takes exactly the same amount. So it doesn't matter how much water we use. We can just kind of put some in and call it good. Okay, so number 3, we're going to want to add some phenolphthalein because this is how we tell what's going on at the microscopic level. When phenolphthalein is pink, that means we have an excess of hydroxide. When it's clear, that means that the solution is more acidic. Okay, so then what we're going to do is we're going to add HCl to the first flask dropwise. We want to stir it to ensure that we're getting good mixing of the acid and base, and simply count how many drops it takes for the solution to become clear. Simple, simple. Repeat that with the other 2 flasks. Okay, so let me expand on that a little bit if you're not following it. So we've got the 3 flasks, and you can see that they have different amounts of hydroxide. Okay, so now imagine how much HCl it's going to take, okay, to turn these solutions clear. Okay, the blue X's represent the hydrogen ion that has neutralized that hydroxide, and we see that the sodium hydroxide needs the most HCl and the barium needs the least, exactly what we predicted before. All right, so let's look at some sample data. Here's our predictions on the left, and let's say that flask 1 took 34 drops, the fewest of all. Oh, well, that means that must be the barium hydroxide. The second flask needed the most drops. Oh, well, that must be sodium hydroxide. And the third flask took the middle, and so that needs KOH. So there you go. I hope that made sense to you. And once again, I hope that this was an opportunity for you to take your existing knowledge of chemistry, stretch it, deepen it a little bit, link it, and weave it together into a tight-knit and comprehensive foundation. So thanks for joining me and good luck on that upcoming test.